Hello everyone, welcome back to another video for the physics series. This time we'll be attempting paper 4.1, October-November 2025. So let's get started. Okay, so here we have question number 1. A train travels with a constant velocity of 56 meters per second on a horizontal track. The mass of the train is 440,000 kilograms. State the difference between the velocity of the train and its speed. Okay. Now, initially, you would say and you would see that they are kind of the same thing, which they are. Magnitude-wise, they are the same. They both carry a magnitude. However, what's different is that velocity, after all, is a vector quantity, which means that it also carries a direction. So, velocity is a vector quantity which carries a direction. Okay, with that out of the way, let's see question number B. Calculate the kinetic energy stored in the moving train. Okay, now to find kinetic energy, then you use this formula here. Ke equals to half mv squared. Now the mass we already know, that is 440,000 kilograms. We don't need to convert anything. And the velocity is 56 meter per second. And then of course we have to square that. If you were to put that into the calculator, then your answer should be about 6.9 times 10 to the power of 8. Now, of course, since this is energy here, it should be in joules. So, 6.9 times 10 to the power of 8. And as you can see, we used two significant figures because all of our values were to two significant figures in the question, like the velocity and the mass. Okay, moving on. The train has a uniform deceleration of 1.2 meters per second squared. Calculate the constant braking force which brings the train to rest. Okay, so here we need to use the infamous Newton's law, F equals to ma, force equals to mass times acceleration. So for the mass, we already know that the mass is 440,000 once again, and then you multiply that by the deceleration being 1.2. Once again, you put this value into your calculator with no need to change any units, and that would be about 5.3 times 10 to the power of 6. Now, since this one is force, then it will be in newtons. So 5.3 times 10 to the power of 6 newtons. Or actually, that should be to the power of 5. Yeah, so to the power of 5. Be careful. Okay, for part 2 here, calculate the distance traveled by the train as it comes to rest. Okay, now for here, you need to identify the formula being d, which is distance, or s for displacement, equals to velocity times time. Okay, now if you notice here, we do not have time. We only have the velocity, v, and we have the acceleration. Okay, so here we need to see from part C, where we need to calculate the constant braking force, which brings the train to rest. So we know that after all, it had come to rest. Because it came to rest, then this will be the final. So final velocity will be 0. And here, 56, that will act as our initial velocity. So what does that mean? So we can actually utilize this when we want to calculate the time. Now we know that acceleration equals to the change of velocity over change of time. Which means that if we want to find the time, or delta t, that will be the change in velocity over the acceleration. So the change of velocity will be final minus initial, so 0 minus 56, over acceleration being negative 1.2. Now it's negative because here it says deceleration rather than acceleration. So there's a bit of a difference. Now if you plug that into the calculator, that should be 14 over 3 or 4.67, or actually 46.67. Okay, so this will be here our time. So now we can actually find the distance, which is s. But what you need to know, however, is that this is the average velocity. So v is the average velocity. You need to know here that we have the rest, right? It's at rest, which means that we need to calculate the velocity, the average velocity. So we have two times. We have the time at rest, so 0, and the initial constant velocity being 56, so plus 56 over time, or over 2, I mean, to get the average, because we are finding for the average velocity. And that would be actually 28. So 28 meters per second. This is the average velocity. So if we want to find the distance, that will be 28 times time being 46.67. And that will come to 1,306. So you can write it as 1,300 meters. Okay, so we write it here, 1,300 meters. Of course, you have to write the units since it's not mentioned in the question or like in the box here. So you need to write the units manually, otherwise you will not be getting the full mark. Okay, so we're done with this question now. Let's go on to question number 2. Figure 2.1 contains information about the planet Mars. Define gravitational field strength. Okay, notice here that it says define rather than just state. If it was state, then you have to actually say the definition, the longer definition that is by words. But here, since it's define here, in physics, define means that you have to rely more on the formula. So gravitational field strength, if we just recall the formula for the weight, then that will be mass times g. So if we want to make the g here, the subject, so W over m. Okay, that would mean that it is the force, because W after all, weight is force, per unit mass, because we're dividing the force by the mass. So initially here, the definition will be force per unit mass. Okay, for part B, an object has a weight of 42 newtons at the surface of the Earth. Calculate the weight of the object at the surface of Mars. Okay, in order for us to do so, we need to find the mass of the object. Here we know that for Earth, the gravitational field strength G is 9.8. Previously it was 10, but now in the current specification of the syllabus, it is 9.8. So we use that. So now, if we want to find the mass, if we derive it from this formula here, then mass will be weight over G. So weight over G being gravitational field strength, so that will be 42 over 9.8. Okay, now if we use that, then that will be about 4.29 kilograms. Now for that, if you want to find the weight, then that will be the mass here, 4.29. But this time, instead of 9.8, we multiply it by the gravitational field strength at the surface of Mars. So times 3.7. And that will give us 15.9 kilograms, or I mean newtons, since it's weight. But however, since here we have all of our values to two significant figures, then should our answer also be two significant figures? Yes, of course, so that will be 16 newtons. Okay, now calculate the volume of Mars. Interesting. Okay, so we have the density and we have the mass, so we can find the volume. Now the density, rho, will equal to the mass, m, over v. So if we derive that and make v the subject, that will be mass over rho, which is the density. So mass is 6.4 times 10 to the power of 23 over the density being 3,900. Okay, and if we calculate that, that should be 1.6 times 10 to the power of 20, the two significant figures. And of course, don't forget the units being meter cubed. So 1.6 times 10 to the power of 20 meter cubed. Now for part C, figure 2.1 shows a space buggy that is tested on Earth. The buggy is traveling at a constant speed in a straight line. The driving force on the buggy is 30 newtons. For part 1, draw and label one arrow on figure 2.1 to show the size and direction of the resistive force on the buggy. Okay, since here it is traveling at constant speed, then here we apply Newton's third law, in which here we will have, or like the opposite side, we will have an equal force to the 30 newtons, which means that it should also have the same length. So we draw another line, like so, and label it 30 newtons as well. Okay, for part 2, a resistance on Mars is less than a resistance on Earth. The same driving force, 30 newtons, is exerted on the buggy on Mars. State the effect that this has on the resultant force on the buggy on Mars. Okay, since air resistance is less than that on Earth, then that means that there will be less drag, less resistant force compared to that of the Earth, which means that the overall force here will be less than 30 newtons. So here they only want us to say the effect on the resultant force, which would mean that the resultant force will be forward. It will be more positive. So we can say there is a resultant force on the driving direction. In which basically I'm saying that the resultant force will be the direction, or at the direction, in which the buggy is facing or driving. Okay, for question number 2 here, or part 2, state the relationship between resistive forces, driving forces, and resultant forces. Okay, now since here we have three forces at once, that means that we can't just say the term directly proportional or inversely proportional. It wouldn't work here. So here we have to form an equation, and this would satisfy a relationship. So, as you know already, resultant force is directly proportional to the driving force, as in if the driving force increased, then the resultant force will increase, and vice versa, of course. However, if the resistive forces increase, then the resultant force will decrease. So if we want to form an equation, then resultant force, I'll just write that a bit more neatly, resultant force will equal to what? So let's say here that the force, instead of it being 30, it was 20. That means that the resultant force will equal to 30 minus 20, which will be 10. So from there alone, we can already see what our equation would look like. It will be the driving force minus the resultant force. Now I'll just undo that, because after all, we have to follow the same and the correct arrow, being 30 Newton. So resultant force equal to the driving force minus the resistive force. Okay, so we're done with that. We're done with question number 2. We can move on to question number 3. Okay, let's see what we have here. Figure 3.1 shows a simplified diagram of a solar cell. Describe the energy transfer in the solar cell. Okay, so after all, it takes in solar energy and then it transfers that into electricity. So here there is, after all, since it's a 2-mark question, this means that there's 2 points to mention here. So like basically we need to mention from where to where does the cell convert energy. So as we said, it transfers light energy or solar energy, but light is a bit more precise. Light energy to, or you can just say to instead of an arrow, light energy to electrical energy. That will do. Yeah. So light energy is like a more, I'd say, general term. Okay, for part B, suggest how the black coating allows the solar cell to transfer more energy. Okay, so black coating, after all, it is a excellent light emitter and also an excellent light absorber. So this will allow it to absorb more light. That's the idea. So black coating is a good light absorber. So more light is absorbed. That's the idea. Okay, we're done with that. On to part C. 0.72 kilowatt of light is incident on the solar cell in figure 3.1. This cell has an efficiency of 75%. Calculate the output power of the cell. Okay, so usually the formula for efficiency would look something like that. It will be output over input times 100, which also can be written in the form of like useful energy over total energy times 100. So if we apply the formula here, after all, that will equal to 75%, then the output by itself will equal to 75 over 100, or 0.75 times the input. Now the total input was 0.72 kilowatt. And to convert that into watts, then that will be times 10 to the power of 3, or 1000. So times 0.72 times 10 to the power of 3. So 0.75 times, let's say 720, if we multiply that by 1000, then that would be 540 watts. That would be the output power. Now state the meaning of the term kilowatt hour. So basically the definition of kilowatt hour. That's the question. That's what the question is saying. So it is the amount of electrical energy transferred by a 1 kilowatt appliance in 1 hour. That's the definition. This one you have to memorize it by heart, as you might see this one often. Now it's been a while since I've seen this question, however, they still ask it, so make sure that you memorize this definition well. For part 3, energy is produced by each solar cell for an average of 6 hours per day. A household uses approximately 7,400 kilowatts of electrical energy per year. Calculate the number of solar cells needed to produce energy for one household. Give your answer as a whole number of solar cells. Okay, to answer this problem, we need to understand or to use the output power here. So we already did calculate the output power, which means that we did calculate the useful power produced. So since that is our useful power in watts, then it will also be wise to convert this to watts, which will be about 7,400,000, or for short, 7.4 times 10 to the power of 6. So if we want to do a calculation, because this one is only per hour. So if we actually want to find for the whole year, then we need to multiply 5,000, or I mean 540 multiplied by 6 for 1 day, and then multiplied by 365 to get the useful power for the whole year. So 540 times 6 times 365, that will be about like 1.18 times 10 to the power of 6. Okay, so now in order for us to get the number of the solar cells, then essentially we need to divide this one over here, which is the household use, which is about 7,400 kilowatts, by the overall useful power. So we need to divide 7.4 times 10 to the power of 6 over 1.18 times 10 to the power of 6, and that will be about 6.27. However, it says that we need to round our number, as a whole number of solar cells. So you can't really have 6 solar cells and a quarter, so you have to round that up to 7. So that's be 7. 7 solar cells. Okay, moving on. For question number 4. A 12-volt, 50-watt immersion heater is used to heat 0.15 kg of water in a beaker. The water is initially at room temperature of 20 degrees. The specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. Calculate the energy supplied to raise the temperature of the water from 20 degrees to 58 degrees. Okay, alright. So we know here that energy itself will be equals to mc delta t. That will be in the case, of course, of the energy for the specific heat capacity, when we have a specific heat capacity here. So to get this energy, that'll be the mass, which is 0.15, times the specific heat capacity, which is 4,200, times the change in temperature, being 58 minus 20, which of course will be 38. So again, like that in the calculator, and that should be, if we did everything correctly, will be 2,300 or 23,940 joules. And to do significant figures, that will be 24,000. Okay, hope that's clear. Okay, for part B, the immersion heater is removed from the beaker. One metal rod and one plastic rod are placed in the beaker of hot water as shown in figure 4.1. The rods are at room temperature, which is 20 degrees, before they are placed into the beaker. Okay, we have a 4 marker. So describe how the temperature of point X on each rod changes after the rods are placed in the beaker. Explain your answer. Okay. Okay, so they're just comparing, essentially. They are comparing how the temperature on the rods will compare with just room temperature, which is 20 degrees, in which now here we have hot water. So basically here, since here we have hot water, so the temperature on point X, which is this one here, will increase. Okay, so that's the first point that we can mention. So temperature on point X increases. And of course, we also have to point out to what point X exactly. So in this case, of course, it will be the metal rod, on the metal rod. Okay, so of course the temperature will increase, but we have to explain how. So that will occur by the process of conduction. So heat is transferred throughout via conduction. Okay, but still, conduction occurs in both the plastic rod and the metal rod. So what's so different about the metal rod? Now, because the metal rod is, after all, made from metal, then that means that it has free moving electrons. So when the particles heat up, these free moving electrons will move to other particles and transfer the energy, which will make them heat up. So, free moving electrons in the metal rod transfer the heat energy to the other particles. To the other particles. Okay. And because now we have actually explained the base on what's going on, then now we can actually mention the point where the temperature is increasing. But to be more specific, it also increases by time because, of course, the conduction process and the free moving electrons process, that does have, or like does require time. So temperature increases over time. Temperature increases over time. Okay, so that's that. We are done with question number 4. Let's move on to 5. A dolphin communicates with other dolphins underwater by emitting sounds in the range of 7 to 15 kilohertz. For part A, state the value of the speed of sound in air and state how the speed of sound in water differs from the speed of sound in air. Okay, so we need to state the value of the speed by itself and then how that is different from air. Alright then. So for air, that would be about 330 meters per second to around 350. Both are accepted or within that range. So like the speed in air of sound kind of varies. However, in water, because particles are closer together, then the speed will be faster. So the speed of sound in water is faster. Okay, for part B, state and explain if humans with normal hearing can hear all the sounds emitted by a dolphin. The answer is yes. Now, some of you might be confused because humans can hear from 20 hertz to 20,000 hertz. Or we can convert that into kilohertz, where there's 20 hertz to 20 kilohertz. Now, thing is, this one here, it's not in hertz, it's in kilohertz. So this is 70, or this is 7 kilohertz, 15 kilohertz. Which means that this is 7,000 to 15,000, which is well within the range of humans. 7,000 to 15,000 is within the range. So, humans are able, that's the explanation, humans are able to hear from 20 hertz to 20 kilohertz, or you can write 20,000 hertz if you want to. Okay, now complete table 5.1 to describe differences in loudness and pitch of two differences dolphins sound. Okay, so here we have 14,000 hertz. The amplitude is large, and because the amplitude is large, then the loudness will be large or high. But here, if the amplitude is low, then that means that the loudness will be low. Okay, regarding the pitch, then the higher the sound, or the higher the frequency, then the higher the pitch, which means that the sound will become kind of softer. So, the pitch will be higher, while here the pitch will be lower. Lower. Okay, that's that. For part D, complete the sentences to describe how sound is transmitted through water. Okay, sound waves are made of vibrating plank, which produce compressions and rarefactions. So this is supposed to be vibrating particles. Here, particles. A compression is a region of plank, and rarefaction is a region of plank. Okay, so when there's a compression, then the pressure will be high. So a compression is a region of high pressure. High pressure. Meanwhile, a rarefaction is a region of, of course, the opposite. Since rarefaction is the opposite of compression, then it will be a region of low pressure. Low pressure. Okay, the sound waves travel blank the direction of the vibrations. They travel parallel. Because after all, it is a longitudinal wave. Okay, longitudinal. So, if it was, however, if it was not a longitudinal wave, then it will be perpendicular. So, yeah. Okay, figure 6.1 shows part of an optical fiber used in high-speed broadband communication. State two advantages of using optical fibers in high-speed data transmission compared to electrical signals sent on copper wires. Okay, we can't really say high speed here because it's mentioned here already. So we can say that. However, we can say that more data can be transmitted. So that's one. More data can be transmitted. And the other point that we can say also is the fact that less data can be lost. Like in copper, some data can be lost, but in like optical fibers, less data can be lost. So that's like the advantage also. Less data can be lost. Now I've actually also checked the Munch scheme and I noticed that they do accept the point of like higher rate or like faster. Although here it's written as like high speed. So you can mention that, but just to be safe, it's better that you mention other points as well. Like it's better that you mention points other than the higher rate. Unless if you are not sure, then here you can mention the higher rate of transmission. Okay, the optical fiber is made of glass with a refractive index of 1.4. Calculate the optical or like the critical angle C. Okay, calculate C. So for here, you need to write and draw the formula, which is that C equal to the reciprocal or equals to sine inverse, the reciprocal of 1 over n. Okay, that's the reciprocal of n. So because of that, here we can just plug in the values. N is of course the refractive index. So C itself will equal to sine inverse the reciprocal of 1 over 4, which will, of like 1.4, which is 1 over 1.4. Okay, plug that into the calculator. And that would be 0.79 degrees. However, that's in radians, so I'll have to convert that, which would be actually 45.6, yeah. So 45.6 degrees, that's that. Make sure that your calculator is in degree mode and not in radians. Okay, now state the meaning of a critical angle. Okay, so basically it's the angle, or to be more specific, it's the angle of incidence. So here, angle of incidence, in which the angle of refraction is 90 degrees. So, in which the angle of refraction is 90 degrees. Okay, that should be the model answer, and make sure that you memorize this one because you might see this question quite often. Okay, for part 3, on figure 6.1, label the angle of incidence of the ray of light as it hits the wall of the glass fiber. Okay. Draw the continuation of the ray until it leaves the glass fiber. Okay. So essentially we just want to draw. Okay, so first things first, we need to draw the normal, which would be, this is not the best normal. However, you try to draw it like so. Okay. So it should be parallel with the surface here. It's better if you draw it dotted, but I can't draw it dotted since I'm using a digital pad. However, when you draw the reflection here, it's better if you can use a protractor. You should always bring a protractor to your exam. So when you draw it, this angle here, which I will show you now, just let me correct this angle over here. This angle, these two angles should be approximately the same. Okay? So these two angles should be approximately the same. And then you repeat the same process again here. So you only need to draw the normal one more time. Again, you draw it dotted in your actual exam. And then you should try to make it such that the angle of incidence is the same as the angle of reflection. Okay, so this looks good. This angle is about the same as this angle here. Okay, and that's that. We are done with question number 6. Okay, now on to question number 7, in which here we have a circuit. So figure 7.1 shows a circuit containing a 6-volt battery of cells and 3 identical resistors. For part A, S1 is closed and S2 is open, in which like S is a switch. The current in the ammeter is 0.08 amperes. Calculate the resistance R1. Okay, so since S1 is closed and S2 is open, this means that we can cancel all of that, and we have a series circuit. And in a series circuit, the current will be the same, but not the voltage. The voltage will be split on the two resistors. So 3 volts will go here, that's 3 volts, and the other 3 volts will go here. So to get our resistance here, R, then that will be voltage over the current, which is I. So the voltage will be 3 over the current being 0.08. Okay, keep like that. And the answer should be 37.5 ohms. To the significant figures, that will be 38 ohms. Okay, for part B, S1 and S2 are both closed. Determine the reading on the ammeter. Show you're working. Okay. So basically here, we don't really need to talk about voltage here. Basically, for the resistance, we already know that all of them are identical resistors. So we know that here, this one is 37.5, so as the others. So in order for us to actually get the resistance, or I mean the current, we need to get the overall resistance, the combined resistance. Now the way I get it is like so. So first of all, we know that they're reciprocal, or to find the reciprocal of RT, which is the overall resistance, then that will be 1 over R1 plus 1 over R2. But here, since we have 2 of them on the same branch, then that means that we have R1, R2 plus R3, like so. And since here, we don't really want 1 over RT, we want RT, we can make this whole thing in a reciprocal, like so. That'll be quicker. So if we actually plug in the values, then it will be something like this, 37.5 plus 37.5 plus 37.5. Or you can just do 2 times 37.5, since they are identical after all. And if you were to put that in the calculator, then your answer should be about 25. So we have 25 ohms overall. And then we can find the current. So if resistance equals to the voltage over current, then that means that the current will equal to the voltage over resistance. So that means that if we want to combine everything, then here we have 6 volt supply. So 6 over 25. Now you want to calculate that. So that will be 0.24. So the ammeter reading will be 0.24. That's the way. Okay. Now explain in terms of work done and potential difference why there is a larger heating effect in R3 than R1. R3. Okay, R3. So because R3 is parallel to what? To the power supply, that means that R3 will get 6 volts. And there are no other resistors. Meanwhile, for this first branch, in which we have R1, it has R2 as well in the same branch. So the voltage will be shared between R1 and R2, which means that this one will be 3 volt and this one will be 3 volts. So because here we have a higher voltage, then that means that the heating effect will be higher. Okay? And of course, because the heating, or like because the voltage is higher, then that means that there will be more work done to move the charge carriers. So that would be our points. I'd like to make it in point form because I see that's easier. Though for this specific case, I'll just write it as 1 because it's quite short already. So, potential difference, or like the voltage, in R3 is higher than R1. Because the resistor is parallel to the power supply, of course. Okay, parallel to the power supply. So more work done. Work done. And greater heating effect. So greater heating effect. Okay. Okay, for question number 8, figure 8.1 shows a solenoid. For part A1, draw on figure 8.1 4 complete magnetic field lines that show the pattern and direction of the magnetic field inside and outside of the solenoid. Okay, so to do that, we need to identify the direction, which is done via the battery. So this long end will be the positive end, and this will be the negative end, which means that essentially, using conventional circuit, it will be like so. The direction will be like so, which means that the magnetic field here will go straight through, right in the middle, where it becomes undeflected like so. That will be our first line. Now also, the same goes for the other lines. However, they have a little curve into them, like something along these lines, something like so. Now, of course, this is not a perfect drawing. You should draw a better one if you are able to draw it on a paper. So it should be something like this. Now, why is it curved? It's essentially because here, the field lines go like a full circle, like so. Here. So technically, this part here is also a full circle that goes like so, but we don't draw it for space. The same goes like so here. Now, for this part here, of course, it goes like so, so. Here, the direction is kind of reversed because it does a full 360. So you do not make the mistake of drawing the direction like so, like this. It should be the opposite. So that should be our line. Okay, I think that's perfectly good. Though I'd say that maybe this one is a bit too circular. Maybe you want to draw it something like so. That'll be more accurate. If you'd want to. So yeah, I think that'll be good. Okay, so for part 2, mark a point inside the box in figure 8.1 where the magnetic field is strong. Label this point B. Okay, I'll mark this point here using an X. This one will be B. Now, it will ask me why this is strong, or like how does my diagram show that. Essentially here, at this point, you can see that all the lines are close to each other. And this suggests that the magnetic field lines, or the magnetic field strength is strong. So, the explanation will just essentially be like so. The magnetic field lines are close to each other. Hold on a second because my tablet lagged. The magnetic field lines will be close to each other, or are close to each other. Okay, this question is done, or this part at least. So moving on to part B, figure 8.2 shows a solenoid in an electric circuit for a bell. For part 1, complete the circuit on figure 8.1 with the symbol for a direct current DC power supply. Okay. It will just essentially be like so, just a circle here, another like here, and then you can add the sign if you want to. And that's that. Okay, explain why the soft iron arm pivots, which are these over here, making the striker hit the bell when the switch is closed. Okay, first of all here, this is a switch. The switch here is closed, so that means that the current will pass by. Now when they pass by, maybe we need to actually reverse the direction here. When they pass by here, then essentially the solenoid will work, and this will cause the magnet to work. Now as the magnet works, as we can see here, it will actually pull this magnetic or this metal part here. It will pull it down, so it will hit the bell. But then this is a contact here, so it will also build the contact down with it as well. And if the contact is pulled down, then this part here has no contact with the circuit, which means that it will just the circuit will just close, like there's no electricity. And since there's no electricity going through, the solenoid will not act as a magnet anymore, and so the contact and the metal will go back to position. And then once again, the solenoid will work, magnetic field generated, and then it will pull the metal again. And so it will strike the bell again and cause another ring sound. So that will happen over and over again until the switch is open again. Like this is how the loop works. Okay, so we can explain. This is a very clever question actually. Yeah, I haven't seen this one in a while. Okay, so this actually is split to two parts, part 2 and part 3, this whole explanation. So we assess first on why the initial ring happens, the striker, and then why it goes back to position. Okay, so as we said here, EMF passes through the solenoid, and so of course the magnetic field is generated. And this will cause the metal to just be attracted to the solenoid. So metal is attracted to solenoid. Because after all, it acts as an electromagnet. So this is the first part here, and of course this will mean that the striker will hit the bell, but I don't think that's necessary to write. For part 3, explain why the arm pivot moves back to its original position after the striker hits the bell. Okay, so basically here the contacts will be broken, so no more electricity will pass through, no more EMF, and so the magnetic field will be broken. Or we can say that the solenoid no longer acts as an electromagnet. So that's what we're going to say. Contacts are broken. So no more EMF in the solenoid. And because of that, solenoid does no longer act as an electromagnet. Solenoid no longer acts as an electromagnet. Okay, that's done. Moving on to question number 9. For part A, describe the structure of an atom of helium-4 2He. Okay, so essentially here, for this atom, we need to describe the protons and the neutrons. So for helium here, essentially, as you can see here, since we do not have any charge here, this would mean that after all, there are also two electrons. So we can describe first of all the nucleus. So nucleus contains protons and neutrons. We can mention how many protons, how many neutrons. So we have two protons. This is evident by this part here. And two neutrons. And this is evident, of course, by the 4 over here. Because as you can see, 4 is total of proton and neutron. So you have 2 plus 2, so you have 4. And also we have 2 electrons in the outer shell. Okay, that's done. Moving on. For part B, the Sun is a medium-sized star powered by nuclear fusion reactions which releases energy. State what happens during nuclear fusion reactions which form helium. Okay, so to form helium we need hydrogen. So all this is a 2 marker. It can be explained in one sentence only. So hydrogen, or like two hydrogen atoms or nuclei joined together, or like you can say fuse together also, that's more accurate, fuse. So they will, hence the name of course fusion. So they will fuse together to form helium. Now my tablet is not doing very good now. To form helium. Okay, that's good. Now for part 2, state two regions of the electromagnetic spectrum by which the sun radiates most of its energy. Okay, two regions. Now for here are the regions in which basically it radiates the most energy. That will be the infrared, the visible light, and ultrasound, or I mean like ultraviolet. So these will be the most radiation coming from the sun. So you can choose either. You can choose infrared or visible light. You can choose infrared and ultraviolet. You can choose a visible light and ultraviolet. It's up to you. I will choose infrared and visible light. So infrared and visible light. Okay, on to part C. Describe what happens to a star when most of the fuel in its center has been converted to helium. Alright, okay. Now here you have actually, since you have 2 points, you have to mention both scenarios. It's either the star is small, or like medium, or the star is large. If it's medium, then it will form just only a red giant. However, if it's like larger, then it will form a red supergiant. So I'd say that small star forms a red giant, only red giant, while larger stars form red supergiants. Okay, now on to question number 10, the last one. Figure 10 shows the orbit of the Earth and the orbit of a comet around the Sun. State which orbit, A or B, is the orbit of the comet and explain your answer. Okay, so a comet, that would be B, and this will be due to the slingshot effect. Okay, so for a comet, the sun is not in the center of the orbit. So basically it will take this ellipse path. So that's what we're going to say. The explanation is that the sun is not in the center of the orbit. Okay, for part B, describe and explain how the motion of the comet changes as it orbits the sun. Okay, so basically here, this is a slingshot effect I mean, is that when it becomes closer to the sun, it will gain kinetic energy, and so it will increase in speed, and as it leaves the sun, then essentially it will have a slingshot effect where it will kind of be launched there, like further apart. So the way that we will say it in scientific term will be like so. Essentially, the comet increases in speed as it is closer to the sun, and then we explain why this happens. And this is of course as the GPE, the gravitational potential energy, decreases and the kinetic energy increases. You can just shorten it down by GPE. GPE decreases while kinetic energy increases, resulting in a slingshot effect. Okay, I think that's good. So we can just move on to the next part, for part C. At one position in its orbit, the comet is 6.6 times 10 to the power of -6 light years away from the sun. State the meaning of a light year. Okay, it's basically the distance traveled by light in a year. Okay, so the distance traveled by light, if you want, you can just say the speed, just like at 3.0 times 10 to the power of 8 meter per second in a year. Okay, that works. Now for the last question, C2. Determine the distance in meters between the comet and the Earth. Okay, essentially they're just asking to convert the light years into meters, essentially. Now 1 light year is 9.5 times 10 to the power of 15 meters, okay? So if we want to convert that into light years, we just simply multiply. So 9.5 times 10 to the power of 15 here, multiplied by 6.6 times 10 to the power of negative 6. Let's see what we will get. Okay, and we will get 6.27 times 10 to the power of 10. And two significant figures, that will be 6.3 times 10 to the power of 10. And since here we already have the unit here being in meters, you don't need to write anything. And that's that. We are done with this full paper. So once again, as I will tell you, if there were any questions that you weren't so sure about, or you didn't get it right the first time when you did your first walkthrough, then maybe you should redo it again, and then see if you got the hang out of it. So that's it. See you all in the next one. Goodbye.